to introduce Peter Chen, who is a PhD student from MIT, and he works in the intersection of data systems and natural language processing. He's advised by Mike Caffarella, who's a longtime friend of AI2, and also works with Dan Roth, one of our scientific advisory board members, among a variety of other luminaries. So very excited to hear about your work, Peter. Take it away.
Cool. Yeah, so hi everyone, I'm Peter and I'm a third-year PhD student at MIT. So today I'm very pleased and honored to be here and share some of my recent work on how to optimize LLM retrieval and reasoning frameworks. So we know that LLMs are good at a bunch of tasks like question answering, math and science problems, code generation, translation, and also games. So to me, it seems like the two kind of meta tasks really involves around the idea of retrieval, where LLMs need to identify what's relevant and keep up-to-date information. And secondly is the idea of after you have that information, to be able to reasoning about those information to perform logical thinking and stuff. So there are existing frameworks proposed for either of these tasks. For example, some of the retrieval frameworks proposed are retrieve then re-rank, where you would have a user query and then you give it to some less powerful retrievers but extremely quick, such as BM25 or embedding-based models. And then you after you have a broader set of candidates, and then you give it to LLM to do some further re-ranking. There are also more broader and more powerful frameworks like those that combine retrieval and reasoning, such as the agentic React-style reasoning frameworks, where once the user query goes in, you'll start this iterative loop of retrieve from some external database or document store, and then reason about what you retrieve, and then further propose follow-ups and stuff if you cannot find the correct answer in a few steps. However, the question is while these frameworks are kind of intuitive and easy to implement, are they efficient and are they optimized in terms of both efficiency and accuracy? So in this talk, I kind of want to bring up some of the my work that addresses and some of the optimization suboptimalities of existing frameworks. So as we kind of preluded earlier, existing agentic system, they would kind of explore this relevant information iteratively, which is inefficient. So therefore, I kind of want to bring in the ability to LLMs to be able to assess and leverage joinability to make it more efficient. Moreover, existing kind of retrieval frameworks that rely on this LLM online re-ranking, they kind of are expensive because they need to do this online analysis each time. So therefore, can we try to do that offline to make it more efficient? And thirdly, I kind of want to argue that existing off-the-shelf LLMs, they handle tasks in isolation, which is inefficient in terms of reasoning because they have to repeat a lot of the computation and reasoning steps. So therefore, we propose another word called log-augmented generation that tries to reuse the prior computation and reasoning. So let me just dive into the first work. So this is a collaboration between some of my colleagues at AWS and also Dan and Mike. So let's imagine this complex question. Naturally, we will identify that there are two main concepts in this question. So therefore, a natural way is to decompose this complex question and then try to search for the relevant parts in the corpus. So then you would probably identify a table that includes one of the concept and then their document that includes the other concept. However, the problem with this retrieval is that if you look closely enough, you'll see that this table and document, they do not have any overlapping information. Thus, they cannot actually be connected to answer the user question. In fact, what you really need to do is to introduce two more tables, although they're not directly mentioned in the user question. However, it's super important to connect the two primary pieces of information together, and that can help to answer the user question if we do this four objects together. So on a high level, therefore, an optimal retrieval system should not only perform information alignment, which is to align the concepts mentioned in the user question to some of the information in the documents or the tables in your corpus, but also do this internal structural alignment that considers the internal data organization of the corpus. So existing works, they focus on information alignment. However, our work will propose that we additionally consider this component of structural alignment. So again, like some quick recap, like with query decomposition using like existing RAG frameworks, you will most likely be able to get like the two tables and documents. However, this does not ensure like a joinability between the stuff that you retrieve. Of course, you can try to like use agentic RAG, which also we kind of mentioned earlier, to like do this like iterative step. So in step number 1, you would try to like find the most populous county in California, and then you search for the keywords. And then you probably come back with like this document, which mentions that like LA County is like the most populous. So therefore, you try to like find like more additional information, like what is the information that contains both eligible free rate and also LA. So then you get that table. However, at this point, what the model will realize is that like the table itself, although it mentions eligible free rate, it does not contain any information about LA. So therefore, it will like continue to search for information that includes like both of these like two pieces of information. But in fact, like the corpus does not include like such information that like such table or document that includes like both aspects. So like this loop might just go on like forever and ever, and there's like no convergence guarantee for like these methods. So therefore, as a quick recap, like what's the issues with like existing methods? For standard RAG with like query decomposition, they do not consider the internal data organization. For agentic RAG, they do kind of like do this implicitly, but again, like this is implicit but not explicit. So and also it's like not really efficient because there's no like convergence guarantees, and typically people deal with is by like setting a hard stop, which is like also not really that ideal. So what we propose is the idea of like alignment-oriented retrieval method that considers two perspectives. One is like what existing work do is that to do this like information alignment, like aligning the concepts mentioning the user question to like the stuff in your corpus. But also like consider this more important like structural alignment part, which tries to align the query to the internal data organization. So how does our method work? In the step 1, it still like do this like traditional thing of like trying to do like query decomposition and align it to like different documents or like tables or other like modalities of objects in your collection. But secondly, like what we do is like different. For each of the primary object that we retrieve, we will introduce some of its like most joinable neighbors or like most compatible neighbors. And then we'll use like some ILP solver to connect like all the pieces of like objects together to form what we call like one draft of complete like joinable set of objects.
Sorry, one clarification question. So the stuff that you're structurally aligning, is that query dependent, or could you do this entirely like in advance, independent of the query?
Yes, so you can definitely do it offline, but the search space will be much larger.
I see.
Because like imagine you have like 1 million objects and you try to like do this like pairwise kind of compatibility detection or like joinability detection. That's like a huge space that you have to pre-compute. However, what we're doing here is that we do this like all joinability or like discovery thing on the fly. So, and because the search space is like much smaller, it's like much more tangible.
Okay, but the actual structural alignment task doesn't use the query when you're deciding, do these structurally align and how?
Yeah.
Okay.
Yeah.
Thanks.
But yes, you can do it offline to like speed up your online process.
Okay.
Or you can like cache the online part and then you in the store and then you reuse it in the future.
Okay.
Yeah. So once we have like those like one draft or like one candidate set of like objects, connected objects, like this is not the only way we can expand the primary set of objects. You can imagine like we introduce 2 neighbors or like 3 neighbors, or we do it for multiple times, in which case we'll have like multiple drafts. So once we have the multiple drafts, what we do is then we finally feed it to like LLM to do like some self-verification aggregation, where we ask the LLM to select the objects based on like the relevance, obviously between the user question and the object content, but also like more importantly, the compatibility between the different objects. And then finally, we do like a weighted voting using the model logits because we treat it as like a proxy for model confidence. And then we finally return the top K objects with the highest votes. So in terms of experiments, we do it we try our method on like the multimodal kind of retrieval data sets, like 2-wiki multi-hop, BERT, and then like the OTT-QA, which involves a spectrum of like tables and documents. And then we compare our baselines, compare our method with baselines such as the standard RAG with like query decomposition, as well as React-style agentic RAG systems. So some of the metrics that we use are like, obviously for retrieval, we measure the precision of recall in F1, but also I think kind of interesting, we also measure this idea of like perfect recall, because we find that like recall can sometimes be misleading. So for example, if you have a recall of like 70%, that doesn't necessarily mean that you have a high quality retrieval, because that can literally just means that for each of the question, you retrieve only 70% of the code objects that's needed. Whereas for perfect recall, it really just means that like, do you retrieve all the code objects that's needed? We also measure the end-to-end query performance. So for the short answers like two-wiki multi-hop and also the OTT QA, we measure the exact match. And then for SQL statement, we actually run it and then measures like how correct or how accurate the output is. And we also, in terms of efficiency, measure the monetary cost by tracking the number of like input and output tokens, and then use like the existing like pricing policies to like try to measure like how expensive each method is. So as a high-level takeaway, I think our method outperforms existing baselines on kind of all the data sets, and then we also retrieve a much smaller number of objects and uses like only one iteration compared to, for example, React that needs a lot more iterations. And therefore, like we also achieve a much higher end-to-end performance, and we do it also at a much lower cost. Because React needs to do this like iterative loop of multiple iterations, but we only, again, do it only once. Cool. I just want to pause here for a little bit and see if there's any questions.
So if I missed this, the neighbors that you retrieve for a given object, is it dependent on the other objects and the other retrieved?
Yes.
Object? Okay.
Yes. So once we have the primary kind of set of objects that's informationally wise relevant to the query, we'll start from those primary objects to expand.
But based on the other ones?
Based on the other ones, yes. And also based on like how relevant your kind of expanded object is relevant to the query. Like obviously you can.
Or the queries?
Yeah.
So, I mean, the one thing that was kind of bugging me from the beginning of this is that question, right? The example question seemed, I mean, it's definitely multi-hop. It seems sort of contrived. Like, I have a hard time believing there are a lot of real questions that look quite like that, right? Where it's like, it's essentially I need to find some unnamed county and then determine something about it. It's in a separate data store. So I guess what's your impression of how these kinds of multi-hop questions look in practice? And do you think your methods would still work well on, a more real query workload? And by the way, I mean, I could be wrong that like, actually there is a real population of queries that looks just like the one you showed. So feel free to correct me if I'm wrong, but yeah, I mean, I'm curious what you think about how realistic these tasks are and whether your methods extend to realistic cases.
Yeah, so I think like the only reason why we pick like multi-hop like QA data sets or like in general like text to SQL is because they involve like multiple data objects to answer the question. It's less on the fact that like the question, like what's in the question. Because like our method works the best when there are like multiple objects that's involved in solving the question, right? So it's more concerned about what's the internal data organization rather than the query itself. So even for this more, I guess, a more realistic question, if like the information that's needed to answer that question is like dispersed, then like all what I'm saying applies.
Yeah, okay, got it. I guess maybe part of what what's motivating my question is that the decomposition seems like it could often be very difficult. It's like thinking about like scientific question answering, for example, like the way a query decomposes is actually quite hard to define. Whereas, the example you showed, I feel like what was maybe easier to decompose. So I guess how often are the errors you make due to an erroneous query decomposition, or do you get that right all the time?
Yes. I totally agree with where you're coming from, but I guess again, it's a limitation of the data set that we're using that kind of makes the step of query decomposition like easy. But I guess like at the end of the day, you don't necessarily need to like do this like decomposition like too accurately, because even if you just retrieve like one like primary object to begin with, our method still applies in the sense that you can still like extend the primary object with its neighbors.
Okay.
If that makes sense.
Yeah, no, I think it does. Yeah, and so, right, it'd be interesting to try your method on a bunch of other query workloads. Sure. Okay. But yeah, great.
Okay, cool. Yeah, so sorry if that doesn't fully answer your question, but we can talk about it also.
No, thank you.
Okay, so kind of the second pieces I want to talk about is like how do we tackle some of the online expensive like re-ranking methods, and how do we like bring that process offline rather than online to make it like more efficient and maybe like enhance its accuracy. Again, it's collaboration with like Mike and Dan. So back to our like previous example, it seems like existing retrieval methods that kind of do rely on like query decomposition or like using existing like embedding models, they already like do pretty well. If we like, for example, put aside that joinability issue for a little bit. Existing like MTab leaderboards also suggest that like existing like dense retrieval methods, they work like really well. But however, is that really the case? I think they kind of overlook this idea of like more complex retrieval tasks, which might be like what you're talking about. So for example, if you have a document that requires like implicit reasoning, which I'll give an example in the next slide, or if you have like more technical tables that includes a lot of like technical jargons and stuff, then existing like dense retrieval methods or embedding-based methods might not actually be working that well. So let me give an example. If the query itself like mentions some queries about like depth perception, but however the document, like the relevant Go document, does not include any like textual hints about like depth perception, then the embedding like models or like existing BM25 methods that rely on this idea of like lexical match or like lexically semantic similarity will fail. So we tried it on like some of the standard of the art like embedding models, and it ranks very lowly. And similarly with some of the technical tables, for example, this one that mentions the security, but it doesn't really mentions the idea of like trading or like stock values or like financial asset. Again, like if the user asks something about like tradings and financial asset, then it would also rank really low. So really, this seems like a semantic gap between the query and the stuff in our data collection. And so what existing methods they would leverage is LLM's reasoning capabilities to like bridge this gap. So between the query and the final, like let's say top 10 like documents, what they'll do is to first like do this like retrieval, which uses like more like less powerful methods to retrieve a broad set of like documents. And then they ask like LLM to evaluate the relevance between the user query and the document for each pair, and then like re-rank it to finally output like a more smaller subset of documents. However, the problem with like such methods is that this like query document analysis, which is done online, has to happen for each query anew, which incurs very high latency and also cost. Moreover, like such methods are inherently limited by the performance of the stage 1 retrievers. So like if the stage 1 retrievers have a recall of like 70%, then at best, the re-ranker will give an output of 70%. So what we're trying to say is, can we like bring things offline to enrich like each of the objects at an offline stage during ingestion to improve the performance of like stage 1 retrievers, to reduce the online cost and latency, because now you can kind of like optionally do this like re-ranking stuff. So the idea is like pretty straightforward. We took a document and then we like enrich it using some LLMs, again in a query agnostic way. So now if we like feed, for example, the previous document to an LLM, it will output like some summary, which will now mention the idea of depth perception. And similarly for the purpose, it will also mention the idea of depth perception. And we also like do this QA pairs that kind of ask the LLM to produce some like synthetic question answer pairs that will be relevant to might potentially become relevant to the actual user question. So kind of the background like motivation why we deal with like this like three-way enrichment is because we think that summary will kind of distill the most important knowledge, while purpose will kind of illustrate what's like important or like what tasks can this like document or this table serves, and while QA pairs will illustrate some of the example synthetic questions that the document can answer, and thus might be able to provide a more direct signal when we're evaluating the semantic similarity between the actual user question and the document. So similarly, if we like take the table and then like pass this like offline enrichment, we'll again like see the enriched content including more terms like financial asset and trading, and thus have a higher chance of matching with the actual user question. So during like online querying, what we do is that we still like consider the original semantic similarity, but however, we also do a weighted sum between the original semantic similarity and all the enriched indices. And with that, the original document that ranks like very low now become ranked much higher. And similarly for the more technical tables. Again, some of the experiments that we perform are including documents that involves this like property of like implicit reasoning, which is like one of the, I think, more popular data set these days is like Bright. And also the technical tables, which includes like Spire 2, Beaver, and Five. And we also compare it with very like mature and like state-of-the-art like stage 1 retrievers such as BM25, dense retrievers that rank high on the M-type leaderboard, as well as some hybrid approaches between the two, as well as some of the online LLM-based re-ranking methods. And here we consider the judge rank, which is like at the time of when the work was done, it's like ranking it was ranking like the top one on the Bright leaderboard.
So what about like other offline augmentation things like doc to query? I don't know this stuff that well, right? But people have looked at trying to augment document representations in indices. They're kind of similar to your approach.
Yeah, so I think like doc to query, they kind of rely on like a pre-trained or like, sorry, they fine tune the model on the document to like generate some like summaries of it. But however, I think what we're saying here is that we leverage like off the shelf like bigger LLMs to do that.
Okay.
Doesn't Dr. Query also just apply a query generation module? Two different examples.
Sorry, can you elaborate that a little bit?
Dr. Query also just uses, you can use an off-the-shelf query generation module, right? Instead of using an LLM, they use a query generation module, essentially.
Okay.
Right?
I'm not that familiar with like that thing, but yes, I can, like, I should definitely like look more into it like, after the thing. Okay, so some of the metrics that we perform is like, again, like for precision, for retrieval, we do like precision recall F1, and then we also consider the idea of NDCG that do this like relative ranking across the different retrieved objects, so that if the goal objects that ranks higher will have a higher NDCG score. Again, we also consider the token usage by tracking the number of like input and output tokens used by LLMs online, and we treat the number of tokens used as a proxy for latency and cost. So I think like some of the takeaway here is we outperform existing methods in terms of their retrieval performance, and especially on the technical table side. And we also compare our method with like judge rank that does this like online re-ranking thing. And we find that like even if we do not use this online re-ranking, but only do this like offline enrichment, we already kind of outperforms judge rank on both the Bright and the technical table data sets. And also like doing this as a using much fewer number of tokens because we do not need to do that online re-ranking thing anymore.
Sorry, can you go back to the previous slide? I just want to see, I mean, those scores on, oh, sorry, those are table data sets, not Bright.
No, the first one is Bright.
The first one's Bright. And sorry, there was something, you're not doing a re-ranking step when you evaluate on Bright?
Yeah, so if we only consider, so we do two things. Enrich index, like just enrich index is like the one without the online LLM re-ranking.
I see.
And we also do it with the online LLM re-ranking to like further boost the score a little bit.
Got
If that makes sense.
It does, yes, thanks. Okay, got it, thank you.
Right, so if you want to achieve like the most, I guess, optimal performance, you can do our method plus the online ranking, but we're offering an alternative that says, essentially you do not have to do this online ranking, but still like perform on par or maybe even higher than existing methods that only do online ranking, but requires much higher online latency and cost.
Bright has original queries and they have GPT-4 read
Yes.
queries, right? Which one does this use?
Yes, so here for both like judge rank and enrich index, we do use the GPT generated reasoning steps. So that is the only like online computation that we do. We do not do like the query document wise like re-ranking and similarity relevance detection. Okay.
Sorry.
Yeah.
Can you go back one slide? Doesn't BM25 also give you like an NDCG of like 25 on, right? Like if you just use BM25.
Yeah, so we do use BM25, and that's what's in the judge rank.
I'll ask you after.
Yeah.
Keep going, yeah.
Yeah. You're probably referring to like in the leaderboard, they probably have like some BM25 plus like some stuff that
I'm asking if you just use BM25, what is the performance?
yeah, so it's like definitely lower than this thing. So like right. We have the result in the paper, but we can talk about it offline. Okay, so the other thing that we do in terms of the similarity, in terms of like quantifying like how good or like how useful our enrichment is we kind of measure the distribution distance between the query and non-goal objects and the query and goal objects. So like the distribution distance between the two. And we find that actually like after we do this offline enrichment, this semantic similarity or the cosine similarity actually increases, meaning that the retriever models now have an easier time of identifying the goal objects from the non-goal objects. And we also do like an ablation study in terms of like evaluating how important like or how useful like each enrichment is. And we find that like in terms for the bright data set, it seems like the purpose, which kind of describes the whole overall goal or like some of the tasks that the document can solve to be the most useful, and then following by the QA person summary. Whereas for the technical table data sets, it seems like the summary is the most useful, potentially because in summary, like it just explains kind of the technical jargons and tries to make things in more like less technical terms, and thus the dense retrievers will have a better time understanding what's going on. Cool. I'll just like pause here for a second. Okay. So finally, I think that kind of the component I want to mention is like how do we handle some of the other suboptimality for reasoning frameworks. So we know that like existing reasoning frameworks, they handle tasks in isolation, like by default, without like external like memory support or stuff. So we kind of propose this like new idea of can we like augment can we augment like LLM generation through an external log store? So the basic idea is like as follows. We know as humans, when we solve a complex task, we would decompose or like try to like break it down into like smaller chunks or smaller subtasks. So for this like multi-hop question, we would decompose it into like 4 kind of tasks or 4 steps. And then for each of them, we would like try to Google it and then try to like come up with the answer. If we like as humans confront or like encounter like a similar or overlapping question, then we will identify that like some of the parts are new. So therefore we need to like Google it and then redo this like thinking and effort. However, like once we know that there's like some overlapping stuff from what we did earlier, then we will like try to reuse the computation from earlier. And thus this achieves kind of a more efficient way of like solving a complex problem. However, for an LLM, again, if we consider an off-the-shelf LLM, they do not have any like sort of external memory support or like anything. So therefore, they would just like treat these two problems as like completely separate and then repeat the same reasoning from before. So therefore, what we try to propose is like, can we augment existing LLMs with a external log store that tracks and stores previous reasoning traces, so that when a new question comes in, we can retrieve relevant logs to augment the LLM generation. So again, like if we have this same query one as before that comes in, because the log store initially is like empty, so it still like does the same generation of like 4 steps. However, we would encode and store the reasoning traces into the log store. So now, like if the new query comes in that kind of overlaps with the previous query, then we'll retrieve the relevant parts of the previous computation, or like retrieve some relevant logs. And now, like when we generate it, it doesn't need 4 steps anymore, but rather 2 steps with step 2 of the sub-steps being reused. So as a quick kind of high level, like the components of this like lag framework is like pretty simple. First is that we encode and store the log store. We encode and store the previous reasoning traces into a log store. This can be done either online or offline. And then number 2 is that we, when a new question comes in, we retrieve the relevant logs. And then number 3 is like we generate using these retrieved reasoning traces. So one natural idea you might think of is to represent these logs as texts. So if we consider like a conversation history of like previous models for previous tasks, you have like multiple rounds of like user message and assistant messages. So a natural way is to just like store, concatenate like all the past round of reasoning traces or like the assistant messages as like one thing and then just like store it. However, like we have some concerns about this like textual representation. First, because it's noisy. It might include some of the irrelevant stuff or like some of the stuff being repeated multiple times. Number two is that if you have a large n number, like i.e. like a large number of rounds, it might exceed like your context limit, even though we have like some long context LLMs these days. So what we alternatively propose is to represent these logs as KV values. We make the following observation. This is like attention weight that's used in the attention mechanism to produce the KV values for your entire reasoning context. So we observed that for any attention weight, it kind of refers to the importance of a token given its previous token. So therefore, like the KV values of a token is really like a weighted combination of the embeddings of all its prior tokens, and thus it encapsulates much more semantic meaning than just the text token itself. So therefore, we can somehow like encode the full reasoning context, but only select the KV values corresponding to a subset of the tokens, and that still like gives you a weighted sum of all the prior tokens and the context. So now like the problem is like how do we select a subset of the tokens? Because we know that like storing the KV values corresponding to all tokens can take up significant amount of space because they they grow linearly with the number of like tokens, and then the dimension of like each token is also huge. It's a high dimensional vector. So therefore, we want to like store the least amount of tokens that balance between the performance and the storage cost. One idea you can have is to like store the K values corresponding to the tokens of the last round outcome. So by that, I mean, like, for example, in a React agentic setting, you'll either be able to output an answer, or you can propose some of the follow-up queries to the next iteration. So we can maybe only store the tokens, sorry, the K values corresponding to those tokens. Or maybe we can like store the tokens corresponding to the entire like last model response. So as we will show in the few slides in the experiment section, we find that like if we store the K values corresponding to the tokens of the entire last reasoning trace, that seems to perform the best and offers the best performance and storage trade-off. So now that we know that what to store as logs, now let's talk about the retrieval part. So what we inject into the log store besides the K values and like what's in the text is like additional embedding representation of the logs into a log store, so that online, when we face a new query, we can use this like embedding similarity-based method to retrieve the top K most relevant logs. And once we like have the logs back, we need to like generate the new outputs given these like new KV values. So how do we do that? We first know that like existing KV values based on like rope implementation of existing transformers, they're positionally independent. Because like these stored KV values were generated based on the original context of the concatenation of the previous reasoning traces. So therefore, these like KV values cannot be used directly because again, they are based on the previous context. So first we construct, so to cope with that, we first construct a new user context consists of the retrieve logs concatenated and pre-appended to the user prompt. Now we need to like re-encode the positional information of the KV values with respect to like this new context. And some of the background of like how this like positional encoding is like given to the KV values is that they'll first derive the positional IDs of the entire like prompt sequence, and then they'll compute this like theta, which is like dependent on the positional IDs, and use the theta to compute this so-called like rotation matrix or rotary matrix, and then applied it to the key vectors within the KV values to apply this like positional information. So then the idea that we kind of taken from this like iClear paper was we first like strip away this like original positional encoding and then reapply the new positional encoding based on the new context. So how do we do that? I think it's pretty straightforward. We first multiply the original rotary matrix by its inverse to get rid of the original positional encoding, and then we obtain the new like theta prime based on the new positional IDs, and then we use the new theta prime to derive the new rotation matrix, and then multiply it by the key values to re-encode the positional information. Cool. So that's it about, I think, the storage part, about like what to store as logs, how to retrieve logs, and then how to like generate with like the retrieve logs. So some of the experiments and data sets that we focused on like knowledge intensive tasks, such as like open domain multi-QA. We also like do it on reasoning intensive tasks, such as like math and science, like QA data sets. We compare with a bunch of, I think, interesting baselines. So obviously the first one is like standard agentic systems that do not leverage logs. And number two is like we also compare with reflection methods that tries to retrieve logs, but instead of like directly reusing their previous reasoning traces, they would do this like additional step of knowledge distillation and extraction that's like query specific. And we also compare with like existing KV cache methods that does not like distinguish between what's encoded and what's stored. So we just treat them as encoding and storing the same thing, which is the last model response. We also deal a variant of our framework that instead of like represent logs as key values, we represent them as texts. So we also have like two subvariants, which are basically if we store like all the rounds of reasoning traces and provide to models, or we only store and provide to models only the last reasoning trace. So in terms of like how to construct this log store, we randomly split the data set into like 70-30 ratio, where we use like the 70% of the questions to construct the log store, but like where we just run them through like standard agentic system, and then we store the past reasoning traces into the log store. However, we know that to mimic a real life scenario where the ground truths are not like always available, we do not apply any filtering to the logs. But you can imagine like a extension, which is like you do some quality check or like stuff to the logs that you store to derive a more higher quality log store. And then we also use the rest of the 30% of the questions for testing, and we call them like that same set of questions. And then for how do you like set up the LLM, we run everything on the local model because we need to access the internal like KV values. And then we also limit the number of like max reasoning steps, where for multi-hop, because there are usually like up to 4 hops, so we only like give it like up to 8 steps. And then for the math and science questions, we give them like 3 steps. Cool. So I guess like some of the interesting results that you can observe is if we like do not first of all, if we do not distinguish between like the how do we represent logs like as text or as key values, we find that like either version or either variant of our system will outperform standard agentic systems that do not use logs. We also outperform existing like reflection methods. And specifically, the reflection methods that we use here is like a recent paper called Dynamic Cheat Sheet, where they would still like retrieve the top K like relevant logs, but again do this like additional step of distilling or extracting the most relevant information that's relevant to the current query. And we also outperform existing KV cache methods that do not encode the entire reasoning context and does not make a distinction between what's encoded and what's stored. And finally, like within our own framework, we also realized that if we use the key value representation, it's actually more effective than the text version. And I think this is because for key values, you're effectively encoding the entire reasoning context, but you're only storing a much smaller number of tokens. That is different from like, for example, if you store like all the reasoning traces, that includes a lot of noise, or if you only store the last reasoning traces, that like loses all the prior reasoning context. We also observe some of the benefits of like logs in terms of like both efficiency and accuracy. So for example, if we focus on the leftmost diagram on music, then we'll see that like, for example, our system, which is like in the red dots, it only uses like around 2 iterations to achieve this a slightly even higher accuracy compared to like standard agentic systems, which takes like 7 iterations. So that effectively shows that with the same kind of efficiency, we can use like much fewer iterations to do that, which is like much more efficient. And secondly, we can observe that even if we like increase the number of like maximum reasoning steps allowed and lead to the kind of plateau of like both systems, we still observe at the tail some accuracy improvement. And that to us means that like using logs can bring more than just efficiency improvement, but also some sort of like insight reuse and some like knowledge reuse to make previously like incorrect questions or like unsolvable questions to become more correct now. We actually also do that analysis here. So what this shows is a number of like questions that were previously from the standard agentic system that were incorrect to correct, correct to incorrect, and also like unsolvable to correct, and so on and so forth. So in general, we do realize that if we do not apply any filtering to the logs, we get some noise, and that might lead to actually a decrease in performance. But overall, we observe that the net improvement is also like pretty significant, and that's why like this leads to all the sorts of like efficiency and accuracy benefit that was mentioned earlier. We also like kind of preluded this discussion of like trade-off between performance and storage earlier, and we actually do that experiment where we vary like the number of like rounds of reasoning traces and the k values that we store. And I think like most notably, we can like store just the k values corresponding to the last action, so just the answer tokens or like the next follow-up query tokens, and still achieve a good result, even though it's like slightly dropped from if you store the reasoning traces of the entire last round. But this is like come at a much reasonable gigabyte of like storage size. And so I think if you are more space like concerned, then you might opt for this like just storing the last action tokens. And finally, we also do some analysis on like how does the performance get impacted if we like change the number of like logs, and we see that in general, if you just increase the number of logs, it generally gives you like much higher performance. Cool. So I guess that wraps up some of the reasoning frameworks that I kind of wanted to talk about. And finally, I just want to also mention like some of my other projects. So at MIT, so this is a collaboration with Mike Stonebreaker. We do have a new kind of enterprise text-to-SQL data set out, and this is like feel free to like use it.
What do you mean by enterprise?
Like private organization.
Okay.
So now like public tables, web tables. This is like private actually tables from that we have to sign like NDA to get.
Okay.
Yeah.
Cool.
Cool. And so finally, like kind of just to wrap up, I talked about how we addressed kind of the suboptimalities for both like existing LLM retrieval and reasoning frameworks, and we hope to like expand it to like even more kind of tasks. And some of these ideas will also originated from my experience in working like databases and data systems before. Cool. So and you can reach me out at this context.
Thanks very much, Peter. That was really cool stuff. We have a lot of time for questions. Maybe I'll ask one first. So in the log augmented generation work, when you're evaluating on like GPQA, the only logs you use are from the 70% of GPQA, right? Okay, so do you have any intuition of how well like the logs from MMLU Pro would work as a source of knowledge for one of the other data sets?
Yeah, that's a very interesting question. So what we generally observe like within the GPQA, and that might be able to generalize to like across like data set, is even with like the two tasks do not share any direct like the same like subtask of reusing traces, the knowledge or like the kind of the insight that's like embedded within the reasoning of like previous tasks can be reused. So as long as like the two things kind of like are solved, like their problem solving strategies or their like insights are somewhere like overlap, like the model looking at it will become more performant on the new tasks. So in that sense, if some of the GPQA queries or like tasks overlap with some of the MMLU, like not even in the subtask fashion, I do believe like there's a way to just use that and make it like more.
Okay, yeah, I mean, it would be really interesting to know kind of what the numbers are, right? If you use MMLU Pro for GPQA, you know, how close do you get to, you know, the numbers you reported for GPQA with logs? That'd be really cool.
I didn't try it, but I think that's a great thing to try. Yeah.
Are you doing this at a specific layer or multiple layers?
You mean the K values? Yeah, we extract the K values corresponding to all the attention layers.
All of them.
Oh, that's a lot of layers.
That is like for Llama, like it's like 32 layers.
Yeah. Do you have
You only do it for a sub-selection of the token?
Yes.
How do you know which one? Sorry, I might have missed this.
Yeah. So Okay. So like if you have like n rounds of like user messages and assistant messages, right? Like this is like very clear cut. Like what is the user message and assistant message? So we just concatenate all the rounds of assistant messages, which we know like they're assistant messages to begin with.
But for GPQA, isn't it one shot? Why do you have n rounds, right? You have a question and an answer. And
Yeah, like you can try to like ask the model to like decompose it into like subtasks and then solve it agentically. You can also do it like n at least one. It doesn't necessarily mean it has to be larger than one.
But which are the tokens you substitute?
Yeah, so we select the tokens corresponding to the last assistant message. Yeah, and we know like which messages are assistant messages.
So if n equals 1, then it's just all of the text.
Just all of the text. Yeah.
I'm taking a step back from this as someone who doesn't really do RAG on a day-to-day basis or use this kind of generation style or retrieval. And it seems like what this is doing and kind of what the trajectory of these things are is it's trying to bridge both the fact that we have like language as symbols and we have these continuous representations. And I'm wondering if you've thought kind of explicitly about trying to bridge both of those. Right, like we have these continuous representations which do a fantastic job, but like for a lot of things, but we don't do, like things degenerate pretty quickly with them at the same time. And I'm like, I feel like there's something here and that like we should be doing a little bit more for like this particular use case to bridge those two. I don't know if you had a comment on that at all. Right, like it's a half-formed idea.
Yeah, no, I agree. I kind of understand what you're talking about. I think like it's definitely like interesting, and so the kind of the perspective that we're taking here is that we treat like continuous representation as sort of like a semantic compression of your entire much larger reasoning context or traces. Like effectively, one like 1796 vector can encapsulate a much higher semantic meaning than just the token itself, which in text is just the word or like the token itself. It doesn't capture the 1796 vector of meaning. So I do agree that there has to be like some sort of like a middle ground where you leverage this like semantic compression ability of like k values and continuous representation, but again, like you don't want to lose the text version, because like another kind of extension that didn't do at this work is like which tokens do you select? Now we're doing it heuristically. Basically, we're saying, oh, like we think that the last model response is like the most important, or like we think that the tokens corresponding to the follow-up query or like the answers are more important, but can we like look at the attention heat map and then discover like, oh, what tokens are actually more important, or like from a more textual level, like can we do that? Like I think that would be a cool extension.
Well, thank you. You know, there's something here that I think is there, but don't know what to do with yet.
Have you thought about combinations of like the second and third topics of your talk, where you know, as you're processing queries in a RAG-like system, you might be outputting reasoning traces about the content you retrieve, or computing embeddings of the content you retrieve. You could cache that stuff in the same way you're caching logs, and then reuse it for future queries. Just I guess, what are your thoughts on that?
Yes, I actually discussed with one of my lab mates about that, and that's kind of like the future work that I want to work on. So like there, I think what we're saying is, you like, as you said, like you output like all these reasoning traces involving like some documents or like tables that you know. So then like presumably you can like do this like offline enrichment using the reasoning traces that you just produced, and then like give it to like each of the table or document, and use that also in addition to like all the indices that I just proposed as another like potentially in the index to retrieve it. Yeah. And we're also imagining doing it at a combination of like document level, like not just like standalone, like just one document. because your reasoning trace likely involves like multiple documents, like multiple tables.
Mhm.
So now like you're not only enriching just one document, but like a group of documents. So then when you're doing RAG, that actually kind of overlaps with my first project. It's like this idea of like you're retrieving a set of objects, but not just like one isolated pieces of information.
Got it. Makes sense. Other questions? All right, if there aren't other questions, we can, yeah, we can let folks go, but let's thank Peter again for the fun talk. Thanks, everyone. Have a great weekend.